Yes, sure, sure.
Hi, everyone. Happy New Year to all of you. Welcome to the 66th session of the MedAI group exchange sessions, as well as the first one for this year. So this week we have Ali Mottaghi, I hope I'm pronouncing that right, from Stanford, here with
Yes,
us to speak about his work on adapting surgical activity recognition models across operating rooms. Ali is a fifth year PhD student working on AI in healthcare here at Stanford, and he's advised by Serena Young in the Medical AI and Computer Vision Lab. He's mainly interested in developing new methods for more data efficient learning algorithms and has previously worked with Intuitive Surgical as well as Cura Health. So thanks so much, Ali, for joining us today. And I guess before we get started, do you have any preferences on how you'd like to take questions? Is it okay if we interrupt you, or would you like them all at the end?
yes. I would say, of course, that is totally fine. Like, if you actually have any questions, for sure. I probably like also like stop like in the like middle of like the talk if you actually have any questions, for sure, feel free to ask them. But yeah, I think at the end of that, I think for sure, like if you also actually have other questions, that I'll be happy to take it as well. But yeah, thank you so much for the intro and like this opportunity to actually give the talk.
Yeah, absolutely. I guess then without further ado, let me hand it over to Ali and let's make this as interactive as possible.
Amazing. Thank you so much. I appreciate it. Hi everyone, I'm Ali. I'm actually, as Nidas mentioned, I'm actually like a fifth year PhD student, mainly focusing on computer vision in healthcare. And my main, I would say, like uh, area of like interest in research is actually developing data efficient models. So basically, how we can actually utilize like the unlabeled data or like a limited amount of data we have, even from other domains, to actually make reliable and like generalizable models. So in this work, I'm actually going to talk about the work that I was collaborating with Intuitive Surgical during the summer. That we basically like develop like a new activity recognition or basically like a video classification algorithm for surgical settings. So for example, like in operating rooms, we want to understand basically what is going on. So I'm gonna basically like start with kind of like the overall like high level view of like the problem that we are basically like trying to solve. So here's the thing. I think usually what is actually happening is that in the operating room is usual like a pretty, I would say, complex environment that like so many stuff are actually going on there. So one of like the ways that people actually one of the ways that people actually like try to get a like estimate of like basically what things are, how things are basically going, is just basically like installing some sensors and cameras either basically outside, like for example inside the operating room, or actually like at the sides, like kind of like a close-up view from the surgeon. So and with that, I think they can actually like first of all like basically look at the whole workflow of like how things are basically like changing over time, and also like it can actually help to detect like if anything goes wrong. So but at the end of the day, like our job is basically just from different like views that we are getting and videos that we are getting from like different points in the operating room. Our goal is to actually describe and understand like the actions that are happening. You know what I mean? So and like for doing that, I think the first thing that we actually like do naturally is to actually get a pretty large and good high quality data set. So, and this is actually thanks to our collaborators and Intuitive Surgical that we basically captured like around like 500 like videos, full length videos, and each of like these 500 like I would say videos are captured in operating rooms that are uh, basically doing the Da Vinci surgical basically system operation. And like most of them are actually like almost all of like them here are actually the robotic surgery cases. However, I would say that technically like the same sort of like settings do apply honestly even to the open surgery settings. But here we are technically like focusing on like 10 different phases of a surgical basic robotic surgery that we actually have. So for example, like here we specifically have like 10 different actions that you can actually like see on the right. Like for example, like preparing like the sterile, like then basically like trying to when the patient comes in, like trying to dock the robot, and then they basically doing actual like the surgery, like basically rolling back the robot and so on and so forth. So, but I would say that the main technical point that we're tackling is the fact that we actually have two different environments here. So we actually have a one operating room that usually actually like does a certain like sort of like procedures with this certain surgeons, and another operating room which actually has a different layout and usually different procedures and different surgeons. And as you know, like most of the time, what actually happens is that we typically like in machine learning, if you actually like train your model in like one setting, one environment, it does perform pretty well on that, but usually it suffers from the basically lack of generalizability when it comes to deploying that on a new domain. So this is basically also like what we observed. So and we are trying to actually focus our attention on how we can actually adapt from one operating room to the other operating room with less amount of like annotation possible. So and I think so. Here's the thing: the high level, I would say, the high level goal that we actually have here for the surgical identification is actually three main probable purposes that we have. First of all, when we actually do understand what is happening in the operating room, we can actually use that to do workflow analysis. Like actually look at like what the things that are happening, and then we say that so this is probably like the part that is kind of like a bottleneck here in the procedure, and it is holding back the whole like surgical team. Or for example, like this is the part that results in a huge ideal time for the operating room, and so on and so forth. That's actually quite important when it comes to optimizing the workflow and cost for basically hospitals. And the other factor here that's also like important is the skill assessment. So when we actually understand what is happening and like how basically surgeons and nurses and so on and so forth are operating and working to each other with each other, so we can actually get an estimate of like how efficient the whole system is, you know. So and this can actually be used for later on like saying that this team is quite like efficient, like they actually have a pretty good actually output and like pretty good efficiency. But like for example, this team is not that as efficient, probably simply because they don't like work well with each other, or for example, like there are a few, I would say, staff that are kind of like a bottleneck in the workflow. So that's also like the other point. And finally, I think the most important point here is that once the surgical activity recognition models that we have are reliable, we can actually use them for anomaly detection. So we apply them in real time and like see what is happening. And if something is kind of like going wrong, we would immediately, first of all, like notify the staff, or if we need help outside the operating room, basically notifying them as well. And I think this can be actually like pretty useful simply because the operating room, as you know, is a pretty hot, critical like place, and there's so many like stuff like going on, and like a small mistake can actually result in patients like basically like life. So so here's the thing. So what we are basically like here specifically focusing on here is the domain adaptation in action recognition task. So as a kind of like a methodology part, so like the main problem that we are basically like tackling is how we can actually adapt like one activity recognition model, like the model that actually like take the video and outputs the actions that are happening, and adapt it from one domain to the other domain with least amount of data possible. So and so the main actually contribution that we have in this work is a new way of like doing that. Like it's a new like domain adaptation method that is focused on semi-supervised domain adaptation. What it means is that what we are doing is, for example, like consider in this case that we have some unlabeled data on like a new domain that they actually have, and we have a ton of labeled data as well in the original domain, and we're actually adapt that to the new domain with probably like only a few labeled data points in the new domain. It means that, for example, like assume that I actually have hundreds of videos in my first like operating room, and then I actually have again hundreds of videos in the second operating room, but unlabeled. And then I'm gonna basically like label like a few basically videos in the new operating room, like for example, maybe 10% of that or something like that. And still like the goal is to close this gap and still achieve the reasonable performance in the second operating room, despite like not actually having everything labeled there. So And the way that we actually like do that, and I'm actually going to go through that, is basically through utilizing both like some interesting like semi-supervised learning methodologies, as well as some domain adaptation methodologies, as I'm going to basically like talk about next. So this is actually like the overall like high level view of our method. So what is actually happening here is that we have like the source and target. Like for example, we actually have one setting, one like for example like operating room with one distinct like layout, and like a type of like procedures that are actually happening there, and a new one. So we first the thing that we actually do is we basically capture and sample small clips from them. So the videos are pretty long. So like for example, like most of the times the surgeries are hours long. So we just cannot like process them like immediately, the whole video. So we basically chunk that into like a small pieces and use like for example like 32 frames, 64 frames or something like that of like each video. So these are basically like samples. We actually have one sample from the source, one sample from the target. So the next thing that we actually do is after sampling that, we do the augmentation. So we create a new version of the same data point with like, I would say, probably adding some noise to that, like cropping that, resizing that, and also I would say even changing the speed or like a playback speed. So for example, if originally the frame rate is like, for example, a 30 frame per second, we would basically like change it to like 10 frame per second to basically kind of like just make it like faster, like by skipping frames. So in this way, we basically get an augmented version of like the same data point. So it's again like original, like the same number of like frames, but like in a different like shape. So then we have like 4 type of like inputs. And I'm gonna actually like talk more about like them one by one. So first of all, as we actually talked, we have the first thing, which is augmentation. We have a very long and variable length video. So we basically just first sample clips like from them, short clips from them, and then we augment them. So, and the way that we actually augment them for the frame-wise augmentation, we do rand augmentation. Rand is pretty actually a straightforward and a standard like procedure, which is actually just adding some like noise and also like color jitter and like these sort of things to each frame one by one consistently. Other thing that we have is the temporal augmentation. Like for example, like how we can change the playback speed. So anyway, so after that we have a new version of like the data point, which is the augmented version. So maybe I can actually go back to this slide. So we actually have the source clip, the target clip, and the augmented version of these two. So these are basically like 4 streams of data that we have. So then we actually pass all of like these to our model, like to our basic backbone model. That is basically an action recognition model. Like we actually call it F here. It can be almost like any clip-based action recognition model that people use. Like here we are using specifically the transformer. But we have also like done some experiments with stream transformer, i3D, and so on and so forth. Anyway, so it's technically the F here is just like one backbone which takes the clip and then produces the features and the probabilities. So that's the thing. And then the next step is, so after we actually pass all of like these 4 to the model, we get some probability distributions and features. You know what I mean? So the next thing that we are doing is we try to align the distribution of like a source and target. So here's the thing. If you actually look at this, we have like one distribution for the original source, one distribution for the original target, one distribution for the augmented version of the source and target. We have 4 different distributions. What we actually want here is that we want the model not to be very, I would say, not to be very sensitive to this distribution of like a source, or distribution of like the input. So we want to, in practice, have like the expected value of like the output from the source and target to be quite like similar. You know what I mean? So here, for example, we can actually see that for the source model is usually more confident, you know what I mean? So it actually can understand what is happening. But for the target, most of the time a little bit like less certain. But at the same time, we want to make sure that overall, the output distribution for the source and target are quite similar. And the way that we do that is pretty simple. So we basically, we have like, for example, we keep actually like a queue of like a source examples and target examples and like the probabilities assigned to them. And then first of all, we get the mean, I would say, or average distribution for each of like these. For example, like if I have like the probability distribution for maybe 1,000 clips, then I basically get the average of those, which is like just the mean value. So I have like these two, and I will get this ratio, and I will just multiply any target distribution to this ratio. So at the end of the day, what is happening is that after this normalization, what happens is that the output distribution for the source and target will be in expected value will be similar. You know what I mean? So in practice, for sure, like they are still like different, but what we are basically trying to say is that model should not be depending on basically the source versus target. Like the output, when you actually look at the output, you should not be able to recognize if it is from the domain 1 or domain 2. You know what I mean? So anyway, so there's one thing. And then we basically get the new probabilities. After getting the new probabilities, then the next task is the pseudo labeling. So once we actually do have the probabilities, we then try to generate the pseudo labels based on the most confident ones. So I mean, like it's quite like obvious that sometimes we do have like a pretty good, like after like training on the source and also like the label part of like a target, we usually have like some understanding and like a pretty good estimates of what is actually happening in the target. It's true that for so many of like them, we still like don't know, we are not sure about, but for like also a handful of like examples in the target, we do have a pretty strong opinion. So in those situations, we actually have we set a threshold, like for example, like the confidence that we are interested in, like usually like here in our experience, like 0.9. What it means is that whenever the confidence that we have so here is basically like p hat here is after the normalization and after the alignment. If the confidence that we have after the alignment is more than 90%, we just basically create a pseudo label. You know what I mean? So we basically turn the prediction probability to a pseudo label. Like for example, here's the thing. What is happening here is that we have like the PS and PT. We first align the distribution to get the P hat. And then if the maximum probability is more than, for example, 90% or something like that, then we just create a pseudo label from that. You know what I mean? And it's technically just like a hard label, and then once we actually have the pseudo labels, then the next thing that is also actually quite critical, specifically in our setting, is not only generating pseudo labels, but also making sure that the pseudo labels are basically uniformly balanced. So here's the thing. What actually happens is that most of the times, if you just basically generate pseudo labels from basically from your predictions, the model is certain about like a few classes, or for example, a few scenarios, and it's going to generate so many pseudo labels on those. And also like it's not certain about like the other ones, and it's not going to generate anything almost for them. And in this way, you are technically generating pseudo labels that are highly imbalanced, and they're basically kind of like highly imbalanced toward the dominant class. And in this case, what happens is that the model, even though the model might be actually might be wrong in a few cases, the few cases that might be actually even dominant, then it's gonna generate so many pseudo labels on those wrong cases, and then it's gonna kind of like believe that it's actually correct. You know what I mean? So and it's kind of like it results in a non-stable learning structure. So because of that, what we do is technically after generating pseudo labels, we do sample them. You know what I mean? So we want to actually make sure that like the pseudo labels are not only accurate, like based on like for example the thresholding strategies and distribution alignment strategies that we have, but also they're uniform. Like otherwise, like we are basically training on a highly imbalanced data. So and for doing that, we are actually like doing a pretty I would say a simple basically thing. So we basically again like keep track of like a pseudo labels that are generated like in a queue. Like for example, you can actually think about I'll look at like the last 1,000 pseudo labels that my model has generated and look at the probability distribution for each class. And then I will sample with the inverse of that distribution to just make sure that the output is kind of like uniform. You know what I mean? So what I'm actually like here doing is seeing like, for example, this is the pseudo label that I generated. Then how many pseudo labels of like the exact same type, exact same class I've generated before, and then based on that, based on the inverse of that, I would sample that. So in this way, I will sample more pseudo labels that are less frequent and less pseudo labels that are more frequent. You know what I mean? And at the end of the day, basically in our experiments, we see that like it's quite like uniform. Like it's not perfectly uniform for sure, but it's a pretty good, I would say, measure to make sure that we're not just completely going unstable and unbalanced when it comes to pseudo labels. So anyway, so at the end of the day, I think the whole like methodology is quite simple. So what we do is, again, like just to wrap it up, so we actually have the source and we have the target. So we first like augment both of them, the source and target, and we pass that to the backbone model, like the model that we have. And after that, we get like the probability distributions for each of like them. We first basically align the distributions from the original version. So I think the other important point here that I actually probably need to clarify is that we basically use the original version of clips, like for example, like the XS and XT, to come up with the probabilities and align the distributions and come up with the pseudo label. However, after coming up with the labels, we actually only backpropagate and generate the loss through the augmented version to make sure that we are not overfitting. You know what I mean? So we basically use the unaugmented original version only for the sake of understanding the distributions and generating pseudo labels that are accurate and basically uniform and so on and so forth. But after so for example, for the source, we already have the labels. We only backpropagate through the augmented version. Yeah. And also for the target, once we have a pseudo label, we only backpropagate to the augmented version. If we don't have a pseudo label, we just ignore that. So at the end of the day, our loss function is like this. So what's happening is that we actually have a loss for the source and target. For the source, it's pretty simple. We have the label for the source. You just basically get this branch, like the first branch, which is the augmented version. And then we get the probabilities and we have the labels, just the cross entropy loss that is as well. So anyway, so it's for the source, and then for the target, it's quite like a little like more complicated. So for the target, what we do is that we actually pass this on basically augmented version of the source and target, to the model to get the probability distributions. We align them, we generate pseudo labels, we sample that, and once the pseudo label is actually ready and basically pass through that sampling and basically masking, I would say, a pipeline, then we actually have it. So technically we have a label, you know what I mean? At that point, we just have a label and we just backpropagate through the model. So that's why that here, for example, we actually, first of all, have a stop gradient, simply because we don't want the gradients to backpropagate through the unaugmented versions. We want gradients to only backpropagate through the augmented versions. So, and then we have the mask and the sample. So the mask is basically saying that whenever the probability is more than our confidence, like for example, 90%, we just mask that, you know what I mean? So for the ones that we're not sure, we just don't use the pseudo label. So that's one thing. And the sampling is basically just saying that based on like the previous pseudo labels that are generated, I want to make sure that I have a pretty uniform distribution of like a pseudo label. So if, for example, you are generating so many of like the pseudo labels of a dominant class, the sample would be like, for so many cases, it would be 0, and it won't be actually backpropagated through, and it won't affect like the model. So anyway, at the end of the day, we actually have the loss of source and loss of target and one hyperparameter. That this is also quite like interesting how we can basically accept this hyperparameter. One important quick point here is that this hyperparameter, it's not completely fixed over the course of the training. It's actually, in fact, at the beginning of the training, we want this lambda to be small, simply because the model is still like very much uncertain about like what is actually happening in the source and the target. So probably most of the time the predictions are not that accurate. So we basically set the lambda to be pretty small at the beginning. But once the model is getting more confident, once the model is kind of like completely learning the source, it's kind of like a pretty solid performance on the source, then we start to increase the lambda. In that case, I think the model is basically tending toward more and more learning from the target. And at the very beginning, what happens is that it learns from the most, I would say, promising examples in the target, that's kind of like certain about, like probably it has seen very similar examples in the source already. So it's pretty confident in those. So it's going to basically see those and we generate pseudo labels for them. It learns that. And then as it's basically seeing more and more data points labeled on the target, it's getting even more confident and is basically pseudo labeling more stuff. You know what I mean? So we gradually also increase the lambda toward the end of the training. So here's the next point here is that what if, for example, we have a semi-supervised generalization? So here, the thing that I was basically talking about was technically unsupervised generalization. What it means is that the source is fully labeled, the target is fully unlabeled. So what it means is that like technically on the target we know the data distribution, but we have no clue about like the annotations and like, for example, like the label distribution. However, for the semi-supervised setting, it says it's a little bit like more generalized version of that. It says that we, for example, might have 10% of like those data points in the target you label. It's actually like a pretty practical scenario. For example, like many companies, like when they want to actually implement like these sort of like algorithms, they do that, for example, on one setting, on one operating room, on one, for example, hospital or whatever, and that works pretty well. But they want to adapt that to a new hospital. They know that probably without any, I would say, annotated data, probably the performance is not going to be perfect. It's not going to be at the minimum performance that is required for, like, for example, implement. For example, it's probably very hard to do a really good job, like, for example, 90% or something like that on a brand new data. So their strategy is, for example, like saying that in this new domain, I would probably capture a lot of like unlabeled since it's cheap. Like you can actually just put cameras there and get unlabeled data. And then I would probably just annotate like maybe a few videos there only. You know what I mean? And like the goal is to basically based on only a few labeled examples and this much unlabeled data and also like the labeled source to close this gap and still achieve a pretty solid performance on the target. So this kind of like the goal. And in this case, when we have the labeled part of like a target, it's technically just another supervised loss that is added to the target. You know what I mean? So technically, in this case, the model from the very beginning has a little bit like more examples on the target. So it's a little bit like even more confident about like the stuff that are happening there. And it usually generates better, I would say, pseudo labels. And as a result, like better model that is going to be generalizable. But anyway, so at the end of the day, when we actually have the semi-supervised generalization compared to the unsupervised generalization, we have an additional loss there. So it's in addition to the source, which is completely labeled, we have a small portion of the target which is also labeled, and we have a cross entropy loss for that as well. So we just add it. So this is basically like the overall like training strategy. However, the other challenge that we actually had in this project is the case of long untrained videos. So the thing here is that usually surgical videos are super long, so what happens is that, like, for example, we actually have an hour, like maybe 2 hours or something like that video. And technically it's not possible to process the whole video at once. It's technically almost impossible to remember because we technically cannot fit the whole video into one GPU. It's just not possible. So anyway, so because of that, what we do is that like the strategy that most of the time people use is to have a two-step training approach. So we first train a backbone model, like a clip-based model. You know what I mean? Like, for example, like we first sample short video clips from the original like data point, original like a long video. And then we train a clip-based model on those short clips. So we first train those. And then after training that backbone kind of, like a clip-based model, we extract features for all the frames. And that feature is the kind of like a condensed version of like the whole video. And that can actually fit on GPU. You know what I mean? So then I think we use those features to feed it to another like temporal model, like that can be like LSTM transform or whatever. And then from like that temporal model, we are generating the boundaries and the classes for each frame. So in this way, first of all, we are still actually using all of like the basically stuff like interesting stuff that they actually have for clip-based models. Like we actually can utilize all of like them. And at the same time, the model at the very end also sees the whole thing. You know what I mean? And based on that, it can actually decide on the exact like precise basically transition frames, from like one task to the other one. So anyway, so at the end of the day, what happens is that we have a two-step training approach here as well. And the most important point here is that we are technically utilizing the semi-supervised adaptation mainly in the backbone setting. You know what I mean? When we actually have like one data point sample from source and target, we want to actually make sure that the backbone that we have is unbiased. We want to actually make sure that the backbone that we have is consistent between source and target. And once it is consistent, once the feature is pretty good, like then we actually just train a temporal model on top of that and we get the final outputs. So yeah, the next thing is actually talking about the experiment. So let's see. So here's the thing. For the experiments, usually what we do care about is the basically the action recognition benchmark, which is usually like the mean average precision. So we have like the original ground truth, like saying that, for example, from this time to this time was, for example, a serial prep, like from this time to this time was the patient in, and so on and so forth. And then we have the predicted version as well, And by comparing these two, we compute the mean average precision. So this is kind of like the standard metric, that a final metric that people use. And in addition to that, we also actually use another metric, which is the accuracy of the clip-based model. When it is given a balanced, I would say, samples from the source and target. So we technically have two metrics here. One is the mean average precision on the whole video, and the other one is the accuracy on the clips, on the sample clips. So we actually have these two main, I would say, metrics for evaluation. And we have like a few baselines as well. So the most fundamental baseline that exists, like I would say for semi-supervised learning, domain attention, and so on and so forth, is just a supervised learning baseline. You know what I mean? So if you don't do anything, you just basically whatever data that you have, which is labeled, just train on those, and like basically just get rid of like anything on label. It's gonna be supervised baseline. It's still like an important baseline to always consider. And then the other baselines that we have is the MCD, so the MCD is actually, like, I would say, to be fair, it's a quite like a standard like benchmark in the unsupervised meditation setting. So what it is I technically it's basically like you're basically trying to minimize the discrepancy between the source and the target feature. So what happens is that we have like the source and target, we pass that through the model, we get the features, and we train an additional encoder on top, like we turn an additional classifier on top, which takes the features and then tries to like basically predict whether it's from source and target. And by actually like training in an adversarial way, trying to fool that classifier, we are hoping to get some features that are aligned between source and target. So it's kind of like a pretty standard like baseline that they still like use in basically domain adaptation. And the other approach that's also like a pretty solid and it's really good is called like MME, like mean max entropy, which is technically specifically focused on semi-supervised adaptation. So it doesn't have that like a equivalent approach in unsupervised setting. However, it basically, to be fair, it's technically just kind of like combining some ideas from a few shot learning, what it means specifically for prototypes, to domain adaptation, and then trying to come up with first of all like generating some prototypes for each of like the classes, and then minimize the entropy of basically the ones that are in the same class. You know what I mean? When actually have a pretty dense classes, minimize the ones that are in the same class and max entropy for the ones that are in the other classes. So anyway, so this is how MME works. And then I think we actually have basically our experiment. So here's the thing. For the unsupervised, we have two main experiments, unsupervised adaptation and semi-supervised adaptation. So for the unsupervised setting, what happens is that we have, for example, since we actually had two operating rooms at the beginning, so we have two experiments going from OR1 to OR2, or OR2 to OR1. So these are basically the two experiments that we have. And we report both the accuracy of the backbone as well as the mean AP of the temporal model. You know what I mean? So they have basically two parts of in the model. Like they have a backbone, which basically takes one clip and predicts whether like the class like for that clip, and also one temporal model, which takes actually all the features from the backbone and then predicts all the actions at the end. You know, so we report the mean AP for that. We have these methods of like supervised MCD and MME, and as you can see for sure, what is actually happening is that by utilizing, despite actually like being a pretty simple approach, by utilizing the pseudo labels and utilizing them when needed, you know, like when they are pretty accurate, when we are confident about that, and also after sampling that to make sure that they are, I would say, they're consistent and like they're uniformly distributed. We actually get a pretty reasonable, like a good boost in our performance, you know. So technically, even in the unsupervised orientation, what it means is that, for example, if you actually look at this, for example, R2 to R1, you can see that we technically have like 6% or like more than that performance boost from technically no like additional like label data, you know. It's basically just more of like the data already exists. It's just basically trying to generate pseudo labels for the most accurate ones and utilize them. So that's the thing. And then I think the next important point is just the semi-supervised orientation experiments. So in this setting, what happens is that we actually, so what we do here is that we first sample like a subset of like a target data set. So for example, here's the thing. We have 2% of the target sample. Like for example, I think our target, I think it was 200 or something like that videos. So we change the percentage of that is labeled. You know, for example, 2% of that being labeled, you know, like for example, maybe 4 videos or something like that, 4% of that being labeled, and so on and so forth. And then in these different scenarios, we compare the performance. For sure, like as we get more data on the target, for sure, like the performance should increase, you know what I mean? So since we have more data, it should definitely help us. But at the same time, as you can actually like see, specifically when it comes to the low data regime, like for example, when it comes to the scenarios that we technically don't have like that much data on the target, even like a small percentage of the data, it helps a lot. You know, like for example, you can actually see that going from the supervised baseline to our method, it's a pretty reasonable jump. Like, you know what I mean? Technically, we actually have only 2% of like the whole data set labeled. You know, it's very small compared to the whole, but still, it gives us a pretty reasonable jump. But at the same time, as you know, like as we get more and more target data points labeled, technically, the value of like pseudo labels are getting less and less. You know why? Simply because we already know enough about the target. You know what I mean? We already know, do have enough data points there, do have enough label data points there. So the model is already pretty reasonable and pretty accurate there. But on the low data regime, when we don't have like that much data points, it is a pretty reasonable gain, you know, like that we get, for example, from only like 2% of like the data set being labeled and rest of them being unlabeled. And also we have the MCD and MME. And as you can see, the MCD is actually quite reasonably working, but not that much actually in the semi-supervised setting. But the MME that is specifically designed for semi-supervised orientation, it's actually working better. However, one of like the main limitations of MME is the fact that they do not generate pseudo labels, and we do. You know, and I think this is probably the biggest, I would say, difference and like the biggest reason for this the gain that they actually have. And I think when we actually like did some more experiments, we find out that also the pseudo labels that we're generating usually are pretty accurate. You know, like when we are setting the pseudo labels confidence to be like 90% or something like that, and at the same time we sample like pseudo labels, usually the resulted distribution of the pseudo labels are not only accurate but also pretty uniform. So it is actually like a pretty good data to train on. You know, so and then also we are reporting the mean AP as well for the temporal model. So here what happens is that it's kind of like the same thing, but since you know, like our model is basically 2-part, you know, like we have one basically backbone, clip-based backbone, and one temporal model. So we basically report the performance of both of them. And as you can see, technically, the usually when it comes, for example, when the model does know the surrounding information from the video, is usually even easier. for the model to actually predict things correctly. You know what I mean? So technically, the temporal model usually has an easier job compared to the clip-based model. So because the clip-based model only sees a short clip, like for example, 32 frames, 64 frames, or something like that of the whole video, and that's it. But the temporal model sees technically like the whole picture of like the video, you know, and how things are changing. So usually because of that, the performances are a little bit like higher in the temporal model, and but still we actually have the same, I would say, order of like the performances between these methods. And at the end of the day, I think one important point here is that what are the main critical parts of the model that is actually working really well compared to the ones that are basically not that much useful. So here's the thing. If we do like some ablation studies on two main parts of like the model, you know. So here's the thing. Maybe I can actually go back to this slide, you know, like look at this. So here's, we actually have technically two main strategies here that are actually pretty useful. That we actually have specifically in our method compared to other ones. The first one that is quite important is distribution alignment, how we align the distributions, you know what I mean? So there's also like a chance of like not doing distribution alignment, basically like you literally using the prediction of the target and then basically generating pseudo limits without taking into account how different distributions in the source and target are. So this is one thing. So one component that we do some ablation is the distribution alignment. And the other component is the pseudo labeling, is basically how we sample pseudo labels. Is that sampling actually helpful, or if you actually just don't sample, it's going to be just fine. So based on these, we actually have these ablations. So we have like 4 different cases. We have only pseudo labeling. So when we actually don't have distribution alignment and sampling, we technically just pseudo label everything. You know what I mean? So just pseudo label everything. And we basically just train on the pseudo labels for all of them. And we get the performance, like accuracy and mean AP. And usually what happens is that actually, if you train on all the pseudo labels without selecting the ones that are accurate and also like making sure that it's uniform, it usually even not only like doesn't help like the performance, but also in some cases it might hurt the performance. So because you are training on so many, I would say, noisy data points, you know, so it's not helping. But the other thing here is when it comes to the distribution alignment, so when we do distribution alignment, but we don't do the sampling, you know, so we, like, for example, it's kind of like the setting that some other semi-supervised adaptation methods also like propose to how we can actually like align the distribution, like for example here at a match, that how we can align the distributions, and based on that alignment, we generate pseudo labels. However, if in this case, we are not doing any sampling, whenever the whenever the prediction is above like 0.9 or something like that, we just generate the pseudo label, even though it might be like very ununiform and unknown. So it's one of the other thing. And the final part here is that what if we do sample pseudo labels, but we don't do alignment? You know, so in the final setting, what happens is that we are basically generating pseudo labels technically for everything. However, after generating pseudo labels, we sample them to make sure that it's uniform, you know, without taking into account how confident the model is, you know. And because of that, I think the good point here is that it's more stable, like the training is more stable. However, the accuracy is not as good, simply because there are so many like wrong pseudo labels, you know what I mean, that they have here. And finally, like for the scenarios that they actually have both of them, you know what I mean? They have the not only basically aligning the distributions, but also like sampling like the pseudo labels to make sure that they are uniform. And as we can see for sure, like this is kind of like the one that has a really huge gain. Like I would say that technically, so here's the thing. I think kind of like if you actually want to have probably one takeaway from like the whole talk is more about, you know, like generally speaking, when you are doing semi-supervised learning and domain adaptation, simply because you don't have that much of a data and like that much of like the input and feedback on the target domain, it's really hard to make sure that the model is, and this basically the whole training is stabilized. You know what I mean? So there's one, I would say, pitfall that happens a lot in, I would say, even like self-supervised learning, even unsupervised learning and these sort of things, that when you actually don't have that much of a strong signal then the model may actually do something wrong, and based on that wrong thing, it generates pseudo labels, wrong pseudo labels, and is going to train on wrong pseudo labels and going way more wrong, just in rabbit hole, So basically, one important point here is that whenever you are basically like doing some semi-supervised learning or domain adaptation and so on and so forth, it's very important to always keep in mind that we need to have some feedback. We need to actually have some measure of making sure that the model is not just basically going through a wrong direction and like being destabilized. And the way that we are technically doing that is with two, I would say, main tools here that you're using. The distribution alignment, we want to make sure that even though that, for example, they actually have the source and target and model might be actually certain about like some of like the target examples, we want to make sure that overall the distribution of like the output distribution of the source and target, they do match. It's an important like criteria that you want to fix. You know what I mean? So it's kind of like a one feedback, and the other feedback is sampling. If the model is basically generating so many pseudo labels of like all the of one dominant class, we do the sampling to make sure that this is kind of like penalizing the model for generating so many pseudo labels in one class and not generating for other classes. You know what I mean? So technically, I think these two are the most important points to make sure that the whole training is stable. You know what I mean? So the model is actually gradually learning and not, for example, like one very, I would say, common problem is that we usually have, for example, in semi-supervised learning, we might have an easy class and dominant class. So the model is just very certain about that. You know what I mean? So like by default, it's pretty certain and like pretty accurate on that. It's going to generate all the syllables on that class. You know what I mean? Or even like, for example, it's going to assign all the other classes to that class, the dominant class. So in this way, we have a highly imbalanced and also inaccurate pseudo labels. And by training on those, the model is even getting worse. It's even getting more confident about like that wrong prediction. So it's quite like important to make sure that we need to have a good like pseudo labeling strategy, and we need to pick what pseudo labels we are using. You know what I mean? Like using everything won't help. So the other thing that I actually want to talk briefly about like is basically different strategies for pseudo labeling. And here I think so. Here's the thing. Like the main strategy that here we used was just a simple like I would say threshold. Like would set like, for example, 0.9, and that's it. So whenever the prediction is above 0.9, we're using that. If not, we're not using that. So, but there are actually like other like approaches that we also tried, and it's also quite nice. For example, like one different like approach is basically setting that confidence and that threshold based on the overall prediction and overall confidence of the model. So I think the problem with like setting a one single threshold is that at the beginning, the model is not confident about anything. And because of that, you're just not using any sort of label at all. You know what I mean? So, but the way to solve that is that, for example, like looking at like, for example, at each stage, at each step of the training, what is the maximum confidence of the model? At that stage might be 0.8 actually. It might not be actually even 0.9. At that stage, the model is usually uncertain. So even the maximum confidence is 0.8. So, and then using that 0.8 and multiplying that by 0.9 that we, for example, like previously had as a zero, and then setting this as a confidence margin that we want. Or even like the other strategy that we also tried is that we actually call it like relative pseudo labeling, like based on like the other samples and each stage, what is the kind of like the relative confidence that we have. If this example is among the confident ones, like for example, if it's usually among like the top 10% of the confidence, we use that. If not, we don't use it, no matter like the actual confidence level. This is one way. And the other way is basically using the adaptive thresholding, which is basically doing that for each different class. And specifically in the scenarios that we have two different, like for example, we have like very different distribution for the different classes. So some classes are quite simple, some of them are quite hard. Then having one single threshold for all the classes, it's not that reasonable. Instead actually using the adaptive strategy might be better. In that scenarios, when it comes to the dominant class, we want the model to be really certain, like more than 99% certain. But on the other side, when it comes to like the ones that are like not that much common, even if the model is like 0.8 certain about that, it is still a good thing. You know what I mean? It worth like training on. simply because the model at the end of the day is going to learn something from that, compared to like just not being trained on that. Anyway, so we actually also like find out that this actually, this can also like these new strategies can also like help, specifically in the scenario that we are looking at the temporal model, like in some senses. So here's the thing. When it comes to the backbone performance simply because it's measured on the balanced input. Because of that, usually we don't see a huge gain when it comes to, like, for example, adaptive thresholding and so on and so forth. But when we do basically test on the original videos with the completely unbalanced distribution, for example, like in our videos, we have a huge number of frames dedicated to mainly just the surgery, the actual surgery, compared to all the other parts, like, for example, like docking the robot, like rolling back and these sort of things. And because of like this imbalance, then I think this is the part that we have like very few, for example, from like some uncommon classes, like, for example, docking the robot, or for example, like moving the patient in, and so on and so forth. And in those scenarios, these adaptive strategies would help a lot. And overall, it would basically achieve a better performance on the whole video, not the clip base. So anyway, so this is basically also what we did. And if you want to actually wrap the whole thing up, and I would basically open that up for questions. So here we actually studied the generalizability of surgical workflow analysis models. And one important actual point that I want to mention here at the end is that it's true that we specifically focused on surgical workflow analysis, but the approach that we have is quite, I would say, it's quite general. Like you can actually like even think about like using that in, I would say, for example, even other like like, for example, image classification, or even like video classification tasks. So the fundamental part of like that, which is basically any classification task that you have, technically can benefit from that. And also, like, the other thing here is that we basically also like showed that how important just basically simple approach like just generating pseudo label is to generate better performance. So the main criteria here is just not only generating pseudo labels, simple, because generating pseudo labels is pretty simple and everybody can actually do that. It's just making sure that the pseudo labels are accurate and balanced. If you basically make sure that these two are correct, you are generating pseudo labels are not only accurate overall, not 100% accurate, but I'm like 90% or something like that accurate, and also like balanced, not like completely heavy tailed and long tail distribution. So in those scenarios, it's even like a very simple approach of just basically generating pseudo labels and selecting from them would help a lot. So at the end of the day, I think we actually are also actually working on a new version of this model also on other tasks other than just like surgical activity recognition, simply because this is something that technically can be used in any classification task. You know what I mean? So technically, even if you actually look at the specific our method, it's kind of like completely model agnostic. So it doesn't matter if like the input is actually like, for example, a clip, or for example, a text or image or something like that. As far as we actually have a classification task, it should work. So that actually like also opens up new areas. That's also exciting, simply because I think basically semi-supervised adaptation is one area that I think is very practical, and like so many, I would say, people are trying to actually work on that. This is gonna reduce the cost a lot, and like we have so many like different tasks that we can actually apply the machine learning and deep learning on. But for sure, we don't have a large data set on all of them. So it's important to be able to actually adapt to new ones with a little bit like data. So yeah, that's pretty much all of it. Thank you so much for taking your time for listening to this talk. You can actually scan this QR code and access the paper if you're interested that we basically published in MedAI. And yeah, feel free to also ask any question that you have over email, and I'll be happy to also like take any questions right now. Thank you.
Awesome. Thanks so much, Ali. I mean, it was a pretty great talk and
No problem.
covered comprehensive things about unsupervised domain adaptation as well as
No problem.
So yeah, let me open up the floor.
No problem, of course.
Yeah, I guess before we open up the floor, maybe just a round of virtual applause for Ali. So thanks again, Ali. And yeah.
No problem.
If folks have any questions, please go ahead and unmute yourself and ask. I can actually get started with a question. So it was very interesting that like the pseudo labeling was like the most interesting part of this entire architecture. I was wondering if you also considered things like an active learning scenario where you might want to like adaptively label videos, and any thoughts on that?
Yeah, yes. I mean, that's actually like an excellent question. I would say that I was actually like just interested. I was actually working on active learning even before that. So I was working on a few projects on active learning. And I think active learning for sure is very interesting and can be kind of like even applied in the same sort of like scenarios. You can actually like think about like of technically doing the semi-supervised adaptation instead of like randomly choosing and picking like the 10% of like the data points or like 5% of data points on the target and labeling them, actively doing that. You know what I mean? So I think it's actually like pretty cool. However, I think there are two, I would say, main probably points that I want to clarify. First of all, I think technically my understanding is that active learning is quite like orthogonal to the actual semi-supervised learning. So technically, so here's the thing. I think one part in the active learning is that how we can actually get the most informative examples, and the other part about semi-supervised learning and domain adaptation is that how we can get the most in training the model based on the data that we have. You know what I mean? So technically, you can actually like think about it this way, that you can technically use and integrate other active learning methods into that as well, instead of like randomly selecting stuff, like doing that with active learning. You know, so it's something that's possible. You know what I mean? So without like any change. So it's technically anytime. So here's the thing: the workflow would be like that. So you basically select 5%, randomly select 5%, label that, and then train the model in this way, and then use that model and the active learning strategy that you have to select the next 5%, and then label that and so on and so forth. You know what I mean? So it's technically possible. And the other thing that I think is quite like, is more of a practical concern is that, I think active learning for sure is very interesting and promising, but it's honestly very hard to implement in practice. So the thing here is that you need to actually have a pretty close loop feedback. So there's actually one, in most of the companies, there's actually one team who is actually labeling and one team that's engineering. You know what I mean? So if technically, hypothetically, it's possible to connect these two and coordinate really well, but it's not super easy either. You know what I mean? So sometimes in some scenarios, actually, it's just way easier and cheaper to just randomly select something and label that. Unless your basic distribution is highly imbalanced and you have to actually sample stuff and have a representative example. But if your input distribution is already kind of like reasonably balanced, it is gonna help, but in many scenarios, it just doesn't cost reasonably. You know what I mean? Like the cost benefits are like not that much on the side of like active learning. So yeah, that's basically my points on it. But yeah, that's actually a great question. Yeah, I think active learning for sure is very cool. Create that. Yeah.
Cool. Thank you. Are there any other questions?
No problem. Yeah.
Yeah, I have one quick question. Sorry, I missed the first part of the talk. I was in another meeting, but
no problem.
Is your actions are very different from the normal action databases that we have?
Yeah, so that's a good question. So I'm gonna go back to this slide, since I think this would be quite nice to look at. So here's the thing. Technically, no, I would say that at the end of the day, our task is action recognition. So the main difference that we have here is just the fact that the original videos are very long. You know what I mean? And variable length, and like I would say we have like different classes with different distributions. But at the end of the day, once we do sample clips from them, no, we do actually sample, for example, 32 frames. And this is just one basically short clip, and it has one single class. It's technically just basically a video classification problem, a clip action recognition problem. So fundamentally, it's not, but there are some like small details that are quite different. Yeah.
And what about the labels? Is your action labels very different from the normal actions label that we have it in open source databases?
That is actually, again, a good question. The short answer, basically this question is no. Technically, it's not. So this basically like the part that I was also like talking about, like that the approach that we wanted to actually propose here is quite general. So it's basically, it can be applied in any action recognition task in general. there are some specific like points about like our data, but to be honest with you, usually we don't actually focus and basically I would say invest on those specific like features in our data. So technically, you can actually like, think that this can be actually applied in other action detection tasks, even on public data sets. And to be honest with you, also like this is basically what I'm working on right now.
Okay. Because I was
so
thinking
these
like
actually
probably,
yeah.
probably distant supervision could also be then used because you have a lot of like action recognition models anyways that can like annotate these clips, but not probably in a very high accuracy. And then you can try your domain adaptation on top of like distant supervision.
Yes. Yeah, I mean, yeah, I think that is true. That is definitely true, and I think there are actually like some interesting points about like something like. So to be honest with you, I think this was basically like a project that I was specifically collaborating with Intuitive Surgical. So I was basically mainly hoping to actually achieve like reasonable performances on their data, but technically the same sort of like scenarios and ideas can be applied on even on the image classification task. You know what I mean?
Okay.
Even in the image classification task, you technically just change your backbone and input data, and everything else should work. You know, so yeah, that's a good question.
Okay, thank you.
No problem. Yeah.
Hi, Ali. Thank you for the great talk.
Yep.
I actually have a question about like how you set the lambda, because I know lambda will be very important. In the beginning of training and in the end of training. So you mentioned that it's a hyperparameter, but you basically do you just scale it up or do you follow like a specific?
Yeah, that is a good question. So I would say honestly, we actually use one kind of like probably like a literature in the domain adaptation that we just basically change that from 0 to 1 based on a cosine, I would say, metric. You know what I mean? So at the very beginning, it basically starts from 0 and then it reaches 1 at the end with the cosine, I would say, function. So it's quite like simple, but like, I mean, it's better to actually do this, you know, like do you actually have this transition to make sure that the model at the very beginning, the model it's basically just not sure about like the target. You know, it may actually generate completely wrong and confident examples. In that way, we don't actually use that data. You know, we don't train on that. We wait and we gradually increase it. So yeah, I mean, like in our case, it was basically as easy as just the cosine, basically, but technically, yeah, there are actually like other ways and also like a couple of like other ones in the literature as well. To be fair, honestly, we didn't actually find that to be very sensitive hyperparameter, but it is important. You know, like the order of that at least is important. You know, like the order of, for example, like I think 1 is quite like optimal, but for example, if you actually have 10, it's like too much. You know, like relying too much on like the target. Or for example, if you actually have 0.1, it's too little. You know, like you are not learning that much from it. So basically, the order of like that lambda is quite like important thing, and also like the fact that at the very beginning you should not rely on that. The predictions are quite long. Yeah.
Got it. Thank you.
No problem. That's a good question. Yes. That's
awesome.
Basically it. Thank you so much.
Yeah. So I guess we are like nearing the end of the talk. So maybe we can pause on the questions for today. But I think if anybody has follow-up questions, feel free to email Ali, or you can reach out to us and we'll put you in touch with him as well. We'll put up the YouTube video later today and we'll let you know Ali as well. But thanks everyone for joining. Amazing. And then see you all next week.
No problem. For sure.
Thank you.
Thank you so much for joining.
Bye.
Take care.